Liquids tend to increase in density as they get colder, and as long as we're not talking about solid ice, this is true of water as well. So what do you predict would happen if we were to put a volume of warm water on top of a volume of cold water? Would they mix together, or would one sink and the other float? Would they stratify into layers? What do you think? In order to perform this experiment, we are going to need 2 containers that are transparent with the same diameter of mouths at the top. I like to use mason jars for this purpose, but you could use drinking glasses just the same. Just don't use stemware because that'll be too unstable. Into the first container, we are going to fill cold water we refrigerated the night before. We're going to fill it all the way up to the top so that we get that nice meniscus hovering over the lip of the container. And then into the second container, we are going to put warm water. In order to do this, we're going to need to put it into the microwave for about 45 seconds. The point is not to bring it up to boiling. If it is steaming, you got it too hot. We only want a nice bath water type temperature. You should be able to put your finger in it at the end. Now I want to make sure that I can tell the difference between my warm water and my cold water, so I'm going to use this hibiscus tea in order to color my warm water. I'm going to give it this nice rich red coloration, but I'm going to save the tea bag for later because I only need the color. I don't actually need to waste all that nice flavoring, so you can make a cup of tea with this afterward. So it's been in the microwave long enough to make it warm, but not scalding. Perfect for our experiment. As you can see here, the surface temperature of my cold water jar is coming up as just under 50 degrees Fahrenheit, 49 degrees Fahrenheit. So that is definitively cooler than room temperature. Meanwhile, the surface temperature of the warm hibiscus tea jar is coming up just under 119 degrees Fahrenheit. This is probably a little bit warmer than you will get in your experiment because I ended up having to reheat it just before the shot because I took so long setting up lights and camera and things like that. So it ended up just a little bit hotter than normal, but the important thing is that it's still not steaming. This is not hot enough to burn yourself. That's very important. There's no reason to have boiling liquids at any point in this experiment. Now this next step is a little bit tricky, so make sure you pay attention and you know what you're about to do before you start doing it. Take a Ziploc bag and you're going to place that bag over top of the warm water jar and then invert the jar so that it's upside down and you're holding the liquid in with the Ziploc bag. Then you're going to take the Ziploc bag and the warm water jar and you're going to place it on top of the cold water jar. Now that's going to cause some of the cold water to spill out over the sides. That is okay. But what you should have at the end is that the warm water jar is sitting upside down on top of the cold water jar with the Ziploc bag in between the two. Next, you're going to slide the Ziploc bag out from between them so that there is no barrier in between the warm water and the cold water. You just have 2 jars sitting on top of each other with 2 volumes of water in contact. Since we went ahead and colorized the warm liquid, we can actually see that there is no mixing occurring between the warm and cold volumes of water. It turns out the density difference is enough to prevent mixing from occurring as long as you don't try to stir it up. This same phenomenon can be observed in large lakes, which stratify into warm and cold layers during certain seasons. Now, how long can these jars actually go on like this without mixing? Well, I've put a clock here in the shot in order to time how long it will take, and I am speeding up this footage to 20 times faster than it actually is. So for every 3 seconds that goes by for you, 1 minute is going by on the clock, and then we'll see what happens after a half an hour. After a half an hour, there has been a very small amount of mixing, but you can still see two distinct volumes of water, the very red one and the fairly clear one. And you can see by the temperature measurements that even if you were to just touch the glasses with the back of your hand, even if we hadn't colorized the liquid, you would still be able to tell which was the warm liquid and which was the cold. So it has remained stratified in these two layers. It's remained separated due to the difference in densities this entire time. Now I'm going to speed this footage up even faster to 30x speed because I left this intact for an additional hour after this point, but you can see even after an hour and a half there's still some more mixing to be done, so it managed to retain its separation even after that much time. Now the next question to ask is what would happen if we inverted the setup? That is, we put the hot water on the bottom and the cold water on top. Use what you learned from the first experiment and what you know about densities in order to make a prediction. Go ahead and pause the video now, and then I will show you that inverted setup in a moment.